Stefania, grazie a voi per essere qua. Io vi parlerò di questa linea di ricerca che abbiamo cominciato 5-6 anni fa insieme al professor Spizzo, con cui condivido la responsabilità del gruppo di nanomagnetismo qui al Dipartimento. Appunto, iniziata 5-6 anni fa, adesso è la nostra principale, forse una delle principali, direi, linee di interesse, ed è sui biomateriali magnetici. Allora, un biomateriale è una sostanza che deve interagire con dei sistemi biologici, quindi sicuramente una proprietà che deve assolutamente avere è la biocompatibilità. Però, dipendendo anche ovviamente dall'applicazione, ci sono altre proprietà molto richieste, che sono una certa leggerezza, il fatto di essere leggero e di avere delle proprietà meccaniche molto buone. Che cosa vuol dire molto buone? Vuol dire che devono essere materiali robusti e soffici, meccanicamente soffici. Questo in realtà è un termine tecnico che potremmo tradurre con elastici o flessibili. Ok, so I switch to English. And the other requirement nowadays, an important requirement, is that they are smart. Smart means that they are able to respond to an external stimulus, which can be temperature, which can be light, ultrasounds, an electric field, and also a magnetic field. Magnetic field is a very very good condition because magnetic field can be actuated fast and above all wirelessly, and penetrate into the tissues without causing damages. And therefore, we are expert on magnetism. We concentrate on magneto-responsive biomaterial. And our approach to produce magneto-responsive biomaterial has been to combine a biopolymer with magnetic nanostructure. For instance, magnetic nanoparticle of some tens of nanometers in size. This is not the only possibility. Depending on the application, you can also produce biomaterials, magnetic biomaterials in the form of particulate system, but using micro particle, for instance. But we point on magnetic nanostructure because they have obviously a small size and therefore a high surface to volume ratio, which we expected could favor the interaction with the biopolymer, and also because of the very peculiar magnetic properties magnetic nanostructure possesses. Therefore, we tried this approach, and actually the research on magneto-responsive materials is really exploded in the last decade. Because they have many applications, for instance, in the field of bionics and soft robotics, and so every type of micro or macro robot has been created, able to mimic biological movement, or also they are employed for the realization of magnetosurgery tools as microcatheter or micro gripper that can navigate into our body under an applied magnetic field. And another field of application is that of regenerative medicine, for instance, for the creation of scaffolds or patches, which essentially are supports for the culture of cells, both in vitro or in vivo. You can build materials that are inserted in our body to develop new tissue. And it has been found out that if you put nanoparticle in these materials and under an applied magnetic field, the cells grow and proliferate in a better way, and also differentiate very fast in the case of stem cells. This is a work we have carried out together with Federico and other collaborators. So, of course, not all is done. There is a lot which can be done, of course, because the search for new materials with enhanced and better performance never stops. And new ideas also of application, one can imagine new application. And the class of biopolymer is quite wide, and therefore one can also have a wide choice. And in particular, we focused on protein-based biopolymers, which are here, and specifically on silk. So you know that natural silk can be produced by silkworms or by spiders. And in both cases, the silk produced is very good, has excellent mechanical properties. The spider silk is maybe the better between these two, is maybe the strongest materials in the world. Much more strong than steel, but it's not possible to have a mass production of spider silk. And therefore, people is searching a new way to produce artificial spider silk fiber. And so we started a collaboration with the group of Anna Rising in Sweden, which is one of the leading group in this topic. And they have found a method which is based on genetic engineering to produce spider silk protein. In short, they convinced some bacteria, Escherichia coli bacteria, if I remember well, to produce the spider silk protein, which is labeled with this particular name. And they also found a very efficient method and also green method to spin the fiber. And this is done by preparing a protein solution, mostly aqueous solution, which is extruded using this syringe into a coagulation bath, which is also bath mainly based on buffered water, where the fiber forms, and therefore they can collect hundreds and hundreds of meters of continuous fiber, which is light, the density is very low, and the typical diameter depends on the syringe, but is some tenths of micron, between 10 and 40, let's say. And so the issue was how to couple this artificial spider silk fiber with the magnetic nanostructure, while preserving the good properties of the two components, namely the good mechanical properties of the fiber and also the magnetic properties of the nanostructure that I'm going to discuss now. And we tried two different strategies. So the first one was to embed magnetite nanoparticle into the fiber. And the other strategy was to coat the surface of the fiber with a thin layer of iron cobalt, which is a ferromagnetic alloy, a nanometric thick layer. And our particular goal was to study the magnetic properties of this system and gain information on the coupling, on the interplay between the two phases that are very different from the chemical and from the mechanical point of view. One is a soft, mechanically soft organic phase, the fiber, and the nanostructure are usually made of an inorganic phase, mechanically hard. Therefore, it's not at all easy to predict how these two components could match. But before starting with what we have, with the research, with this presenting our research, I decided when I prepared this lecture to use a consistent part of my time to explain some key concept of magnetism and nanomagnetism. So it is a choice. I hope that it could be useful. I don't know. Anyway, I start from the very beginning. So what is a ferromagnet? A ferromagnet is a material which is made of atoms which bear a magnetic moments. And the magnetic moments are all parallel aligned by exchange interaction. And therefore, you have a total magnetic moment, and you can define a saturation magnetization, which is given by this expression, the total moment divided by the volume of your ferromagnet. Actually, this is not a realistic situation, because if you have a bulk ferromagnet, namely a piece of iron, a macroscopic piece of iron, bulk ferromagnet is never spontaneously magnetized to saturation, actually. And the reason is that if this were the case, your ferromagnet will produce a magnetic field that extend in the space around the ferromagnet itself. But this is not a favorable situation, because in this case you have high magnetostatic energy. And therefore, to reduce the extension of the field and to reduce the magnetostatic energy, a subdivision into magnetic domain appears in your macroscopic piece of iron, let's say. And in each domain, the magnetization is the saturation magnetization. But the orientation of the magnetization changes from one domain to the other. And therefore, in the most favorable situation, the material is able to completely close the flux, one says, so to completely annihilate the presence of this external field, so reduce to zero the magnetostatic energy, but the material is no more magnetized. The material is demagnetized. It has not net magnetization. And the direction the magnetization is in each domain is along preferential spatial direction. This is an important point. This is a key concept of magnetism, very important, which we call magnetic anisotropy. In a ferromagnet, in the absence of an applied field, the magnetic moments, the atomic magnetic moments, are, and therefore the total magnetization in each domain, are aligned along a preferential spatial direction. Which we call easy axis or easy anisotropy axis or easy magnetization axis. And there are several factors which determine the direction which are the easy axis. For instance, the crystalline structure, the type of Bravais lattice that your ferromagnet possesses, but also the shape of the sample you are considering, and also the presence of an applied mechanical stress, as I will also discuss later. And therefore, if you are in this situation in which the magnetization does not point along an easy axis, for instance, because you are applying a magnetic field which is trying to rotate the magnetization away from the easy axis, there is an energy loaded in your ferromagnet, which is called the anisotropy energy, which in the simplest form is given by this expression, where key is an anisotropy coefficient, which depends on the type of magnetic anisotropy that you are considering, which, let's say, predominate in your ferromagnet above the other. V is the volume of your ferromagnet, and theta is this angle between the easy axis and the magnetization. Therefore, it's clear that the anisotropy is minimized where the angle is zero. Okay. So Of course, if your ferromagnet is subdivided into domain, we have just said it is not a net magnetization, but you can saturate, so align all the magnetic moment of your ferromagnet if you apply a strong enough field. And therefore you reach the saturation. And when you decrease the field back, something very interesting appears, which we all know is the phenomenon of magnetic hysteresis, which means that the magnetization does not revert back to zero, but you have a remanent magnetization. And to annihilate this remanent magnetization, to reduce it to zero, you must apply a negative field, which is called decoercivity. And then you can close the loop if you like. You have a hysteresis loop, a magnetic hysteresis loop. So the shape of this loop, which means the saturating field, the value of the remanence, the value of the decoercivity, is determined by many, many different factors. But an important factor is magnetic anisotropy. And therefore, please try to remember this sentence: the greater is key, the greater is the anisotropy coefficient, and the greater is the decoercivity. Okay? Another important thing that I have to recall is that the ferromagnetic order of the atomic magnetic moment, namely the fact that they are all aligned, parallel aligned, is actually counteracted by thermal energy, therefore by thermal fluctuation. And therefore, a critical temperature exists, which is different for each type of ferromagnet, which is the Curie temperature, above which the ferromagnetic order is lost. Because the fluctuation, the thermal fluctuation, the thermal energy is so high that the magnetic moment are free to flip back in any direction due to thermal fluctuation. And you can try to align again, at least partially, all the magnetic moment if you apply a very, very strong magnetic field. Okay? So what happens when you enter into the nano world, when you reduce the dimension of your ferromagnet to a nanometric size? The first things that happen is that there is no more subdivision into magnetic domain, because of course, also the subdivision into magnetic domain has a cost in terms of energy. And therefore, below a critical dimension, there is no energy gain in the domain formation. Therefore, if you have, for instance, a spherical particle, the critical size depends on the type of the material, but is typically of a few tenths of nanometer. And therefore, a magnetic nanoparticle is a single domain, let's say. And the other important, very important phenomenon is superparamagnetism, and this is a little bit more complicated. So let's consider a nanoparticle, okay, with its magnetic moment, and which is aligned along an easy axis, okay. So this is the expression of the anisotropy energy, which is here, this black curve here. And therefore, the magnetic moment can be oriented in this representation up or down, okay, along the easy axis. And to revert the orientation from up to down, the magnetic moment must overcome this energy barrier, we say it is kV. And you can do this by applying a magnetic field, which helps, let's say, the magnetic moment to reverse its orientation. And therefore, if you measure, if you make a plot of the magnetization versus an applied field, actually you observe a magnetic hysteresis loop. But if the volume of your nanoparticle is really small, it can happen that the energy barrier, the height of the energy barrier, kV, is comparable to the thermal energy of your particle, namely temperature times the Boltzmann constant. And therefore, in this condition, the moment of the nanoparticle is able to overcome the energy barrier, flipping back and forth without the need of an external field. And in this case, you have a superparamagnetic nanoparticle. Namely, you have the moment has the possibility to overcome the energy barrier, I say, even without an external magnetic field. And so in any instant, the moment can point in any direction, okay? So if one looks at this condition, it's clear that a characteristic temperature exists, which is called blocking temperature, that separate the block regime, namely the regime in which the magnetic moments can point only up or down, and this superparamagnetic regime in which the magnetic moment is flipping in any direction randomly. An important note is that usually you are not dealing with just one nanoparticle, but you are considering a population of nanoparticles. And even if your nanoparticles are very good, they are never all identical, but they are distributed in size. And this means that you have a distribution of volume, and therefore you have a distribution of blocking temperature, okay? So all these recalls, I should recall what I've just said a few minutes ago about paramagnetism. But there are important differences between the two phenomena, which are really very different actually. But one difference is easy to understand. In the case of paramagnetism, what was flipping randomly was the magnetic moment of the atoms, okay? And here, what is flipping in all direction is the magnetic moment, the net magnetic moment of a whole nanoparticle, and therefore it's a high magnetic moment, and therefore we speak of superparamagnetism, okay? But as in paramagnetism, if you decrease the field to zero, if you apply the strong field, you are able to magnetize all your assembly of nanoparticles, namely to align in the field direction of the magnetic moment. But when you decrease the field to zero, you won't observe any longer the phenomenon of magnetic hysteresis. So no coercivity, no remanence. And so in short, this means that if you have an assembly of superparamagnetic nanoparticle and you apply a field, you have a high magnetic response. But if you decrease the field, the magnetic response goes to zero. Namely, you can switch on and off the magnetic response by switching on and off the magnetic field. And obviously, this can be quite interesting if you want to make a magnetoresponsive material. So, at last, we can speak of the first class of samples that we have prepared. So, artificial spider silk fibers with magnetic nanoparticle embedded. How to do that? Well, you remember how the artificial spider silk fiber are produced by our colleague in Sweden, and therefore the idea was apparently simple. Okay, let's add some magnetite nanoparticle to the protein solution, and so we will obtain a fiber with embedded magnetic nanoparticle. But things are not so simple because nanoparticles tend to form agglomerates. And not just because they are magnetic and therefore they can interact by dipolar interaction, but all the nanoparticles are strongly interacting and tend to form agglomerate. I mean, even non-magnetic, and mainly due to van der Waals interaction, so electrostatic interaction at the end of the story. And so how to avoid the formation of nanoparticle agglomerates? And the idea is the same using the same stratagem that people use to avoid that any kind of nanoparticle forms agglomerate, namely coating the nanoparticle, which means growing around your magnetic nanoparticle a different phase, a coating of a different phase, obviously non-magnetic, and in general is an inorganic coating. This is done for several reasons in general, including avoiding the formation of aggregates. In the most ambitious case, it is done to promote a binding of drug molecules, for instance, or other biological entities. Therefore, it's something not trivial, something difficult. It's hard work for experts in chemistry. In our case, we wanted to favor the dispersion of the nanoparticle into the spider silk protease solution, which is mainly a water solution. And therefore, we wanted to hydrophilic nanoparticle, okay? But what coating? It's not so easy. There was not an easy answer to this question because nobody did that before. And therefore, what coating? No answer. And therefore, we tested 3 different types of nanoparticle with different coating. DMSA coating, this was an acid. This was APS coated, it was a compound of silicon. And the dextran is also a biopolymer, actually. And this different type of coating also resulted in a different surface charge around the nanoparticles, so negative, positive, and neutral. And the particle also differs for their mean size. Of course, these are distribution of the size of the nanoparticle, and the mean size was different, 70 nanometer, less than 10, and these were quite big, 32 nanometer. And using this type of nanoparticle, actually, we succeeded in our Sweden colleagues succeeded in doing something that they were not able to do using naked nanoparticle, which means really producing meters and meters of continuous fibers. And they also changed the nominal magnetite concentration to the fibers. So starting from the pure fiber, which is white, and then increasing the magnetite concentration, you see that the color changes and goes towards a dark brown. And then started our magnetic characterization, which was quite demanding because, of course, we have a lot of sample. And the first thing we measured, I show a selection of the results to you. So first of all, magnetic loops. We use a squid magnetometer, which is a very powerful instrument, very suitable for this kind of investigation that is here in this department. And we measure the hysteresis loop at 2 different temperatures, 5 and 300 Kelvin degree. The first information that we got from this measurement was to estimate the real fraction of magnetite into the fiber, which not necessarily was the same as the nominal magnetite fraction that we put in the solution. And this is done by comparing the saturation magnetization to the saturation magnetization of the nanoparticle alone that, of course, we also measured. And we found very good agreement in the case of the DMSA-coated nanoparticle, but not in the other 2 cases. In particular, the APS-coated nanoparticle gave the worst results. So the amount of magnetite into the fiber was much less than we expect. And the other thing is that you see at 300 Kelvin degree, we have no magnetic hysteresis in the case of this nanoparticle, of this fiber with the MSA-coated nanoparticle. No hysteresis in this case. In this case, we observe magnetic hysteresis. So for this set of fiber, we expected a superparamagnetic behavior. But remember, the absence of magnetic hysteresis is a necessary but not sufficient condition for superparamagnetism, and therefore we concentrate on these 2 types of fiber to better investigate on superparamagnetism. And here we carried out a quite particular type of measurement. It's a little bit difficult, but I try to explain what we did. You take your sample, which in our case was a bundle of fiber. You put into the magnetometer at 300 Kelvin degree, and then you decrease the temperature under in the presence of a small magnetic field. And when you arrive at the lowest temperature, 5 Kelvin degree, you remove the field, and then and therefore you obtain a remanent magnetization. And then you measure the remanent magnetization without field as a function of an increasing temperature. And for instance, in the case of the DMSA coated nanoparticles, this is what we observed. In this case, all the curves are normalized to the initial remanence value, but what you observe is that the remanence is decreasing. And it's decreasing because with increasing temperature, more and more nanoparticles enter into the superparamagnetic regime. And at room temperature, 300 Kelvin degree, your remanence is completely annihilated, which means that all the nanoparticles really are entered into the superparamagnetic regime. But this is also something more that you can do, because if you make the derivative of this curve, of course, you obtain other curves which pass for a maximum, shows a peak, which show a peak. And this peak, the whole curve is a figure, let's say, of the distribution of blocking temperature in your assembly of nanoparticles which are embedded into the fiber. And the maximum is the mean blocking temperature. And here we obtain very satisfactory results, because in the fiber with the lowest concentration of magnetite, the peak was exactly where we expected, considering magnetite nanoparticle with the size of 70 nanometer, which was the mean size of our distribution. So this means that the particles were well dispersed into the body of the fiber. With increasing the concentration, you observe that the distribution broadens and the maximum shift a little bit to higher temperature. And this is what happens when the nanoparticle of an assembly starts to interact by dipolar interaction. Dipole-dipole interaction. Anyway, the shift is small, and therefore good results. Actually, we obtain a good distribution of the nanoparticles in the fiber, which is not at all to be taken for granted. Especially at low concentration, the nanoparticles are very well homogeneously distributed. Let's see what's happened, how different is the behavior of the fiber with the APS-coated nanoparticle, the ones that gave the worst results in terms of magnetite loaded in the fiber. In this case, it's very incredible behavior, but because all the curves irrespective of the magnetite content are superposed. And the magnetization, the remanent magnetization, is not zero at room temperature, which means that actually not all the superparamagnetic are into the superparamagnetic regime. The nanoparticles are in the superparamagnetic regime. And this is strange, because the predicted value of the blocking temperature for this small nanoparticle, the size was less than 10 nanometer, was around 10 Kelvin. And if you calculate the derivative, of course, again, you have all the curves superposed, but the maximum is at much higher temperature, at 1 order of magnitude larger. And this is a clear indication that your nanoparticles are aggregates. And therefore, they feel very strong dipolar interaction. And so one can conclude that this type of nanoparticle with this coating are not good to be dispersed in the solution. And what happens most likely is that the nanoparticle precipitate when put in the starting aqueous solution, and therefore some magnetite was lost since at the beginning and did not enter into the fiber. Of course, for this type of system, the mechanical properties are very important, and therefore our collaborator measured the mechanical properties by performing tensile tests. And I'm not time to enter into the detail. However, we measure different parameters. The strained break gives information the ductility of the fiber, the strength, of course, of this information, the strength on the robustness of the fiber, and the Young modulus give information the flexibility. And here the blue bar are the results for the fiber without nanoparticle, which actually is not as good as the natural one, but however is one of the best fiber produced by man. And therefore we observe that all the fibers remain ductile, do not become brittle. The mechanical strength is slightly reduced compared to the fiber without nanoparticle, but these are good results. Actually, the order of magnitude does not change. And as regarding the flexibility, this set of fiber is the best one. So in general, the fiber with the MSA coated nanoparticle show the best mechanical properties beside the best magnetic properties. So the second class of system, I should go a little bit fast on the second part, are silk fiber coated with magnetostrictive iron cobalt layer with a nanometric thickness. So here I would like to explain what is a magnetostrictive material. If you have a ferromagnet, so again, a little bit of magnetism. If you have a ferromagnetic sample, is it possible? Not all the ferromagnetic sample shows this behavior, but some ferromagnetic material show this particular phenomenon. If you start from a ferromagnet subdivided into domains, so it's not it's magnetized actually. If you apply an external magnetic field that magnetizes the material, you also observe a change in length of the material of your sample in the direction of the applied field. So if your length increases, so you have a positive magnetostriction, otherwise you have a negative magnetostriction. And at saturation, the magnetostriction is a mechanical deformation, mechanical strain, which is given by this ratio, delta L, divided by the length of your sample. So this strain is small, is a small effect. But it's really has very, very important consequences. And one of these consequences is this: if you have a material with positive magnetostriction and you have your ferromagnet subdivided into domain, and you apply a tensile stress, as shown here, then this axis, the direction in which you apply the tensile stress, become an easy magnetization axis, an easy anisotropy axis. And on the reverse, if you compress your sample, the compressive stress is a hard axis. And this means that by applying an external stress, you give rise to a form of anisotropy, which is called stress anisotropy or magnetoelastic anisotropy. And is given by this expression, namely, the key coefficient, the anisotropy coefficient, is proportional to the saturation magnetostriction and to the stress. Okay? This phenomenology is called magnetomechanical coupling. And therefore, the idea was, okay, let's produce mechanically soft fiber, not only magnetic, namely not only magnetoresponsive, but also able to exhibit magnetomechanical coupling. And this is why we selected iron cobalt, because this alloy is the ferromagnetic alloy with the highest value of MS in the world. And therefore, it's good to have a high magnetic response. But it's also a quite high value of magnetostriction. It has positive magnetostriction. And therefore, we wanted to combine biopolymer and iron cobalt. And this was done by coating a thin layer of iron cobalt around the fiber. I mean, really around one fiber, one piece of fiber of some centimeter, but not around the bundle, just one, which is not at all easy. It's something crazy, actually. But that was the idea, and we tried to do that by using a vapor deposition technique, which is spatter deposition. We have here the apparatus in our lab. It's the leading technique to coat materials or to grow thin film. It's very used also at industrial level, especially in the field of electronic, for instance. Substantially, it means that you have a target which is bombarded by accelerated ions, and therefore some atoms are ejected and move towards a substrate where they form a film. And the fact is that normally the substrate is flat. For instance, a silicon buffer. In this case, it was our micrometric fiber. But the things apparently work well, and this is what we obtain in the case of a thickness of the iron cobalt of 100 nanometer, because actually we prepare 3 different types of fibers with a thickness of the iron cobalt of 5, 10, and 100 nanometer. But here again, is the coating really well coupled to the fiber? We didn't know in principle. The problem is always the strong mechanical contrast between the fiber and the coating. But we can have an answer to this question by performing a magnetic characterization. And here, the suitable technique is also here in the department. It is Moche magnetometry. It's a very particular kind of magnetometry, which is based on the magneto-optical Kerr effect, which means that polarized light reflected from a magnetized surface may change its polarization. And therefore, if you apply a magnetic field which changes the magnetization, you can measure the magnetization changes by looking at the polarization changes. But here again, I'm speaking of one single fiber, okay? One single fiber, a piece of single fiber. So it seems really difficult, but it can be done. And my colleagues, Professor Federico Spizzo is probably the best, the more expert in Moche in Italy, and also his PhD student, our PhD student, Filippo Lanaro, is on the way. Because they succeeded in doing something even more difficult, namely measuring by Moche a strain fiber. Which means that the fiber is put between these 2 arms of this device they prepared, and therefore moving the arms, they can change they can apply a stress. The stress is given by this expression, is the force divided by the cross-sectional area. But actually what we are able, let's say we are able to control is not the stress, but the strain, namely the deformation of the fiber. This is really, this seems impossible, but it can be done, as also with success. Even in this case, I show you just a selection of the results, even because these are unpublished results. And so, for instance, on the fiber 10 with the iron thickness, with iron cobalt 10 nanometer thick, you see, these are 3 different hysteresis loops taken at different value of the strain. So 0, 4%, 8%, And you clearly observe that the hysteresis loop is changing. In particular, the anisotropy, the coercivity is increasing. And this happened because you are with stressing the material, stress anisotropy appears in the fiber. You remember the stress anisotropy coefficient is given by this expression, and therefore with increasing the stress, you are increasing the anisotropy coefficient, but you should remember that the greater is key, the greater is the coercivity, and therefore you see that the coercivity increases. And this is very good results because a really difficult measurement, and therefore it's great satisfaction to succeed in doing this, and because it demonstrates that indeed the strain is transmitted from the fiber to the iron cobalt coating, and this means that there is a very good match between the two components. So the two components, although they are so different from the mechanical point of view, are well coupled. And this transmission actually depends on the thickness of the iron cobalt coating. And therefore here I just show you for three different types of fiber. I compare the hysteresis loop measured as zero strain and I measure it in the strained fiber. And you see that also at zero strain, the fiber are different. I mean, the shape of the hysteresis loop is different. The coercivity is different, even without strain. But when you apply a strain, you observe different behaviors. For instance, in this case, only a strain of 4% is sufficient to more than double the coercivity. But on the other extreme, at 10 nanometer of thickness of the iron cobalt, you can increase the strain, but up to almost 20%, but the change in coercivity is very small. Therefore, the transmission of the strain depends on the thickness of the iron cobalt coating, and this is something that we are still rationalizing, let's say, but what is really important, and that we have succeeded in creating fibers with a magnetic response, but also with stress strain sensitivity. And now just to conclude, I skip the conclusion, but I want just to say that, of course, there is possibility of carrying out thesis work in this argument, in this subject. These are all the instruments that we have here at our labs, and so the magnetron sputtering, the Moche magnetometry, squid magnetometry is also available here. But while these are always on, let's say, squid magnetometry is a highly sophisticated and expensive technique, and therefore we normally organize the temporary session of measurements. If you wanted to, if some of you wanted to visit our lab, you can contact me or Professor Spizzo. We also very often use the facility of the microscopy center here in Unife, which are very good. At the moment, we are working on chitosan. So on chitosan film, we started the production of chitosan films. Chitosan is here. It is also a biopolymer. You may ask about why I didn't speak. You speak so well of silk, and now you are speaking of chitosan. The reason is that also chitosan has very interesting properties. And therefore, we have started this new research. In particular, we are producing film in this case and not fiber. But we can produce here the sample here in the department. And so let me just thank the people. So, of course, Professor Federico Spizzo, and then our PhD student, Filippo, is the poor guy that is working on coated iron cobalt, fiber coated with iron cobalt. Is a second year of PhD. And Francesco is at, where is here, is the first year of PhD and is the poor guy that has started working on chitosan films, which is difficult because when you start a new research line, it's always a little bit complicated. These are all the persons that have collaborated in the research presented. So the Sweden group of Anna Riesing, Gabriele Greco is a young researcher that graduated here in Ferrara, and so once a year he used to come here and speak of spider. Is very fond of spider. And this is the group that prepared the nanoparticle. It's one of the best group in the world in the synthesis of magnetic nanoparticle. And we also collaborated with Professor Pugno from Trento University, that is very good expertise in mechanical properties, and therefore helped us to explain the mechanical results. So thanks for your attention.